I'm in a room where, unbeknownst to me, there was stickiness on the floor, and then I stepped in it, and now everything is sticky. And when I move my feet, it sounds weird and gross. So apologies for that. I'm Michelle, and I wanted to discuss an interesting thought experiment that might help us understand why a priori comparisons, or comparisons that we choose that we're going to do with our data before we look at the means and the results from the F-test, are better than the post hoc or the comparisons that are made after we've had a chance to examine the means and kind of pick and choose what we think we should be taking a look at. So in terms of a thought experiment, we're gonna suppose first that there were 10 comparisons to be made in this imaginary world of data collection. So that would mean we had 5 means to match there being 10 comparisons. So mean 1, mean 2, mean 3, mean 4, and mean 5. And when you examine the 10 comparisons, you could, of course, compare mean 1 to mean 2, or if you wanted mean 1 to mean 3, or mean 1 to mean 4, etc., mean 3 to mean 5, all the way down. So these are just the 10 comparisons kind of listed here to help us out. So there's 2 scenarios in this imaginary world. So the first scenario is that we're going to blindly pick one of these 10 comparisons, and that's going to be the one that, after we analyze our data via an ANOVA, that's going to be that one comparison that we decide to make in this imaginary world. That's a weird way to do an a priori comparison, but of course it's just going to illustrate this point about probabilities that we were discussing in the lesson slides last week. So if you blindly, mindlessly pick one of these 10 comparisons, so I'm going to do it. I'm going to pick that one. Okay, 2 versus 4. So I picked 2 versus 4. Okay, awesome. So that's my kind of blind picking. Okay. So I had a 1 in 10 chance that I was gonna choose that one. I mean, I'm a little short, so maybe ignore the fact that I wasn't really pointing up so much, but in general, if we randomly picked, we'd have a 1 in 10 chance, or a 10% chance of just randomly picking this comparison that we say that we're gonna do once we do our ANOVA. Okay, yeah, sticky floor. So then, scenario 2 is that we would instead look at the means, and then we're gonna pick one comparison that we were gonna do. So it's, instead of randomly choosing one, we're actually going to have a chance to look at the means, assuming that we had a significant F-test too, so that we know that we can happily go ahead with a comparison, I guess. That's kind of a touchy point, but I simplified it. So so scenario 2, examine the means. There's too many colors to pick, and it's kind of this I'm kind of like paralysis by choice. Okay, I'm going with black. Okay, so let's say that x1 was actually 9, and x2 was a mean of 2. And I need to arrange this so that it matches up. And then x3, that would be 7. x4, let's say that was like 25. And x5 could be 50. Okay, cool. So we have these 5 means that we examine, and we're gonna choose a comparison to do now. It's not random anymore. And our human eyes are drawn towards, this kind of, let's look at these potentially significant differences. And so maybe what your eye might be drawn to is, look, here's the smallest mean 2, that's x2, mean 2. And then here's the largest mean, so that's mean 4, okay? Don't know if you know where I'm going with this. So maybe we could argue that if scenario 2 was in effect, we would choose x2 and x4. And we would choose it with certainty because when we get to see the means, this is how we feel led to choose two means to compare, right? Unless we had a theory beforehand that told us otherwise, this is kind of where it goes, right? If you don't know anything about your data other than what's showing you. So we'd have x2 and x4, okay. So then the issue becomes we want to assess the chance of us choosing the comparison x2 versus x4, or mean 2 rather versus mean 4, if scenario 2 is in effect, and it's 100%. Because as I'm arguing, if we have nothing else to base our decision on except for looking at these means, we're gonna go and we're gonna choose this guy. Okay, that's where this 10% a priori versus 100% post hoc comes into effect. It's more of an illustration about like the dangers of being able to see something, and as human brains, human minds, we're like we look for patterns, we look for things, we have our biases. There would definitely be a bias in our field towards wanting a significant result more than likely, right, these days. That's something that you guys will be able to, as younger scientists, help us work on as we progress. But in any case, the 10% chance now inflates to a 100% chance that we're going to choose this comparison. And here's the last bit. So if you've held on for this long through the stickiness and my interesting style, that is fantastic. And so here's the punchline. So what if I then told you that in the actual world, where we can actually say, because it's a thought experiment, see the population means, we knew that mean 2 and mean 4 were equal. Because if we then knew that, we can say not only is there a 10% chance I'm going to choose to compare mean 2 and mean 4, but I can also say there's a 10% chance that, I'm going to end up getting a type 1 error, something that I call a false positive sometimes, if we end up blindly picking that comparison. So at chance, let's say that they were far apart enough. These are the means. They were the means up here too. We just revealed them here. But you didn't know that, so you blindly chose via pointing. And so there's a 10% chance that you end up getting a type 1 error because in reality, the population means are equal. So we would be wrong to reject the null hypothesis. This data has a bit of, say, sampling error associated with it. Some observations have inflated this mean or brought this down in a sense that now when we try to use the sample as representative of the population, unfortunately, we don't have the luck or the on our side or what have you. And the issue that we come up against when we try to do these thought experiments is that we don't ever know the population means, ever. So we don't know when we're false positiving. We set an alpha and we go with that. But the idea with this thought experiment is this allows us to see that there's certain situations where we actually do legitimately, by a bad practice, increase our chances of doing that. Because there are sometimes cases where in the population the means are equal, and by chance they'll be apart, and if by chance they're apart, your eyes will find that difference and want to test that difference, and then you will have 100% chance of, there's a big difference. It's reasonable to think with my example that you are going to find a significant difference between those two means in that comparison. So there's a 100% chance then, theoretically, that you are going to incur a type 1 error. So I don't know if this makes sense. I encourage you to think about it and let us know, let me or the course team know if you have further musings about this. I think this is a very tricky idea, and I've discussed it with colleagues, intelligent colleagues like you, and been confused. My hope is that you'd be able to generate an example on your own then if this wasn't helpful to kind of try to work through it. So that is a follow-up to our post hoc versus a priori, imaginary world 10 versus 100% discussion from class last week. I'm gonna make sticky floor noises while I turn the video off. Bye!